Hey guys, hope everybody's doing okay. What we're going to do right now is take a look at some review materials for the acid-base equilibrium exam. And we're going to start out taking a look at the exam format and a couple things you should focus on as you're preparing for this. So, like most of our exams, it's 20 multiple choice questions. You could expect these to take you about a minute, minute and a half each. There's very little like math that's going to need a calculator for those questions. A few of them may, but the majority of them should be able to be done without a calculator. So some conceptual problems and some that should involve some easy math or at least mental math or math you can work out quickly without a calculator. Okay, so you can expect there. 4 free response questions. 1 is long, should take about 25 minutes, and the other 3 are short, which should take between 10 and 12, okay, or less, of course. No extended time as usual, so you want to work efficiently. You need to recognize the question, like I have in the next bullet point, and within a few seconds realize what you have to do to solve it. Really for all of our exams, but especially for this one, that problem recognition is key, and then being able to jump right into the problem-solving process is really important. If it takes you 3, 4, 5 minutes to figure out what you need to do and then start working on it, you're never going to get done, and you're going to leave a lot of points available that you could have had. So the only way to do this is to just practice like crazy, all right? That's why I have you doing a lot of FRQs this week in preparation for this. Today we have a lot of practice problems and things that are geared to help you along for this exam, all right? So there's even some optional practice that's on the roadmap that you guys can take a look at. If you really shouldn't think of it as optional, it should probably be mandated practice. It's a couple things I didn't get to in class in terms of some warm-ups or little practice problems that I do have linked there for you along with the answer key. So the more you practice and the more seriously you take the practice, the better you're going to be. Going back to your homeworks, all the homework should be done. All the practice in the packet should be done. There should be there should be no problems here that are left unfinished. And you should be able to look back at those and do some of those again and use those to study for your exam. So redo some of those problems. There's no problem that I ask of you that is that doesn't have a purpose. They're all meant to help you with the end result here of doing well on the acid-base equilibrium exam. So all homework, class examples, notes, warm-ups, and practice FRQs are obviously fair game. So I just wanted to go through that real quick with you. Some exam strategies. I'm just going from the beginning of the unit to the end, so I'm not going to spend a ton of time here because you could read them. But it goes all the way back to identifying acids and bases up here, so it's key knowing how to do that. Along with that, identifying conjugate acids and bases and the strength of those. So knowing that the strength, strong acids and strong bases, you should know exactly what those are. They have negligible conjugates, and if you have a weak acid or a weak base, you have a weak conjugate acid or base as well. So you should know what your 7 strong acids are, and you should know what the strong bases are as well. We talked about those a lot in class. Writing dissociation equations is a must, right? So with and without water, that is important. So you should know what they look like with and without water. So with water, you'll see the H3O plus for some of your acid dissociations, and without the water, you'll just see the H plus. We should recognize that they're the same thing. We didn't do the POGIL this year, but we do have the summary note sheet on strengths of acids. So you should be able to explain what those trends are and identify strong acids out of a grouping, which ones are the strongest and the weakest. Identifying salt solutions as acidic, basic, or neutral. That was our hydrolysis of salts mini lab. Being able to write those equations and packet pages 26 through 29 is extremely important when you talk about titration curves, buffers, and the common ion effect. A lot of math, calculating Ka, Kb, pH, pOH, hydrogen ion, and hydroxide ion concentration. We should be familiar with all of that and make sure we understand that there are no problems that are going to require a quadratic. So you're going to make the assumption a lot in this on this test and really on the AP test in general. Understanding your acid-base titration curves, so being able to identify the category. So our main categories were strong acid, strong base, and weak acid, strong base. There are different categories as well, but they are all can kind of be related back to the ones we have here. So if you have a strong acid and a weak base titration, you should be able to predict where the equivalence point is, or what the pH is at the equivalence point for those as well, based on what you have left at the equivalence point. So these are the two we spent a lot of time on that we should be most familiar with, but just know that there are other types of titrations. There is a review video on the roadmap that isn't too long that might be a good idea to take a look at, just to be familiar with those. The main parts of the titration curve are your initial point. We should know how to figure out the pH there. Half equivalence point is obviously extremely important. We should know our little shortcut there, which is where the pH is equal to the pKa. At the equivalence point, what's the pH? How do we find it? And then after the equivalence point, what's your titration curve going to do? So continuing on with that, particle diagrams, knowing what it looks like at each part of the titration curve is important. So again, that review video linked on the roadmap is key. And then you had a homework assignment, 44 through 46. Is definitely good to revisit that. I would definitely revisit that. It's very, very helpful to go and do that. So that's 44 through 46. Common ion effect. Make sure you write the dissociation equation for the weak electrolyte. I was helping a lot of you in class with some of these problems, and a lot of the issues that we had stemmed from the fact that we were not writing a dissociation equation for the weak electrolyte. And if you look back in your notes for the common ion effect, one of the things that was like literally step number 1 is to find your weak electrolyte and write the dissociation equation. Therefore, we have to know what our solubility rules are. So they're here again for you, but we have group 1 and NH4+1 ions, in addition to onchlorous permanent always being soluble. We should be able to determine the pH change with the common ion effect, so homework page 50, something to take a look at. And then, of course, we wrapped up with buffer solutions. Be able to quickly and accurately identify a buffer solution. We did examples of this in class, so if you see some like this, we have HOBr and NaOBr. You should, within 2 seconds, know it's a buffer solution. Carbonic acid and potassium bicarbonate, within 2 seconds, you should recognize that as a buffer solution. We did one like this in class, ammonium fluoride and ammonia. Again, within 2 seconds, you should recognize that as a buffer solution and progress through your problem. Really, really important right here, writing chemical equations when an acid or base is added to a buffer solution. We did a lot of that in class. It was in the lecture, it was in the homework, and some of the practice problems that we have done. So please make sure you revisit that. And finally, calculations involving buffers. The only equation you should really worry about here is Henderson-Hasselbalch. You should know how to use it, and you should avoid algebra mistakes like some of us are making on the lab quiz that we took. So when you undo your log, you have to make sure you, with the Henderson-Hasselbalch equation, it ends with that log of your conjugate base over the weak acid. You have to make sure you undo your log first and just end up with, if you're solving for one of these components, end up with your fraction on the right. So undo the log first, and then you undo this fraction or solve for something in that fraction. Some of us are making a mistake on that. My period 1 class, if you're watching this, which most of you should be obviously, I may have forgotten this. So this is one of our pages in our packet. I can't exactly remember what page number it is, but it comes right before all the titration notes. Okay. So all the notes on strong acid, strong base, weak acid, strong base titrations, there's a little bit about polyprotic acids. And on your practice test, there are some questions about this as well. So I just wanted to point it out. I did it in some of my classes last week, and I think I ran out of time or forgot to do it for you guys. So anyway, if you have an acid like phosphoric, where you have H3PO4, there are 3 ionizable hydrogens there, or 3 acidic hydrogens. So you're going to have 3 dissociation equations. It's not going to lose all 3 hydrogens all at once. You have H3PO4 dissociating into H plus and H2PO4 minus. This is the dissociation equation without water being shown, obviously. If water was being shown, you would have plus water over here. And then you would also have, this would be H3O plus over here. Okay? Your first Ka value is 7.5 times 10 to the negative third. We should recognize phosphoric acid as weak. So we have a relatively small Ka1 value. Once all of that first hydrogen has been dissociated, we're going to dissociate our second hydrogen. So we have H2PO4 minus producing H plus and HPO4 minus 2. Lose another hydrogen, decrease your charge. Notice the Ka2 value is even smaller. So the Ka1 value has a, this doesn't occur very readily. Losing the second hydrogen occurs even less readily, and losing your third hydrogen, you can see the equation here, is the least readily occurring process of all of them here, if that makes any sense. So the general rule of thumb here is your Ka1 value is always greater than your Ka2 and always greater than your Ka3. It's always more difficult to lose subsequent hydrogens than it is to lose the first one. All right. So if you see a titration curve like this with the polyprotic acid, this is really cool how you have 3 acidic hydrogens and you also have 3 equivalence points. Okay, as if 1 isn't enough, we have 3 here. So you can see the first, second, and third equivalence point happens around, this is an approximation here, closer to 0 milliliters of base being added, and then 50, and then 100. So you can see they're equally spaced apart. All right, so that's what a polyprotic titration curve would look like. Here's one with sulfurous acid. We have 2 equivalence points. Sulfurous is a weak acid with H2SO3. So you have your equivalence point number 1 and equivalence point number 2 here. You can see those on the titration curve. All right, so you should just be familiar with how those look. All right, we're moving on to a couple practice problems here. You can pause the video, take a second or a couple minutes, try to solve these. These are definitely AP level, multiple choice level questions. This is what you should expect to see a lot of on the test. So puts a lot of content and a lot of concepts all together here. So take a look at the first one. Take 2 minutes, try to solve it, and you can unpause the video and we'll go through the solution together. Okay, if you take a look at this first equation here, or this first problem, we have a weak acid dissociation, and it says which of the following species will be at the highest concentration in the solution. So usually you could eliminate 2 choices right off the bat, and you know this is a weak acid titration. The Ka value is extremely small, so that means this is going to be reactant favored. So there's a lot of HCHO2 here. Okay, there's lots of this. Okay, there's very little product. So I know H3O plus is a product, and there's not going to be much. Right, because we have a really small Ka value. So look at that. You already gave yourself a 50-50 chance at this problem if you understand some very, very, very simple foundational information that a small Ka value, and even if that wasn't given to you, you know HCHO2 is a weak acid. So you have very little product, lots of reactant. The question here, though, is what's the pH? It's 1 or 2. Well, it's 2. Those are, you know, if it was like 1 and 6, it'd be easy. You can guess 1, but it's 1 and 2. The too close to just take a guess. So let's actually try to figure it out. If you have your ICY table, and you can see this is the level of mental math that's required of you here. You have HCHO2 yields H plus and CHO2 negative. All right. So do a quick ICY table. See if I have enough room here. Initial molarity was 0.5. We know this is 0, 0. So we have minus x plus x plus x, 0.5 minus x, x, and x. All right. So we know you're never going to have to do the quadratic. So we're going to say this is 0.5. All right. It follows our rule anyway of our assumption. So now let's actually go through and figure this out. So we have our Ka expression, which is 2 times 10 to the negative 4th equals x times x over 0.5. Okay, simple. We have to simplify this. 2 times 10 to the negative 4th times 0.5 gives you 1 times 10 to the negative 4th. And that would equal x times x. All right, 1 times 10 to the negative 4th is x squared. Solve for it, square root, and you get 1 times 10 to the negative 2nd is equal to x. Okay, that is your hydrogen ion concentration. So what's the pH going to be? Well, obviously pH is negative log of hydrogen concentration. So pH is negative log of 1 times 10 to the negative 2nd. I mean, back in our pH and pOH as an 8-minute Ed Puzzle video, this is very, very simple stuff here. The answer is going to be 2, right? So if you have 1 times 10 to the negative something power, that is going to be what your pH is. So it looks like the correct answer is going to be letter D. All right. So that, I mean, that's stretching it there. I mean, it's 2 minutes, okay, to try to do a problem like that. So you want to average around 1.5 minutes per problem. Some are going to take you about 1 minute and some are going to take you 2. So if you take 2 minutes on a multiple choice problem, you need to make up that 30 seconds on a different one. All right, let's try this one. Again, pause it, try it, and then we'll go over it. All right, so for this one, we have a solution containing HCl and a weak acid HClO2. pH is 2.4. You're adding base, KOH. You want to increase the pH to 10.5. The amount of which of the following species increases as the KOH is added. So this is a really easy problem in my opinion if you could visualize what's going on. All right, I'm going to make a beaker. What's in there? I have a solution containing HCl. It's a strong acid, so I have some H+. I also have some Cl-. I have a weak acid, HClO2, which does not dissociate very much. So those are the 3 main species I have in my container. I'm going to add KOH. I'm going to add a boatload of it here. My pH is going from 2.4 all the way to 10.5. So I'm going to add a ton of KOH, and I'm going to see which one of the species here is increasing. So let's think about it. First of all, I'm going to eliminate A because nothing is really reacting with the Cl. All right. You're going to say, well, maybe the K+1 is, because KOH is going to dissociate. So you're going to end up with K+ and OH- ions in here as well. So these are all the ions floating around. You're going to say, well, maybe KCl is going to come together. But you should recognize KCl as being, first of all, completely soluble. Second of all, there's no more, there's no way for the Cl to increase. Like, where's more coming from? So A makes no sense at all. We can also get rid of, a couple other ones here, really. We can get rid of H+. All right. Again, it says, which of the following species increases? Well, the H+ is going to react with the OH-, right? So you're going to have H+ plus OH- producing water. So the H+ is coming out of solution, which makes perfect sense. Like, the H+ is actually decreasing. Okay, the Cl- is staying the same. H+ is decreasing because it's combining with the hydroxide to create water. All right, so all that reacts. Okay, the K+1, Cl-1 aren't doing much of anything. And I mean, you're adding enough KOH to make this pH go through the roof. All right, so it goes all the way up to 10.5. So that means eventually all the hydrogen's gone. Okay, because it reacted here with the hydroxide to make water. So what are we left with? We're left with HClO2 plus the rest of the hydroxide we're adding to make our pH go, crazy here. So if we take a look at what we are doing with that equation, we have HClO2 plus OH-. That's going to produce water, H2O, plus ClO2-. So look what's happening. The acid is reacting with the hydroxide, so this is going down, so that's wrong. And it's going to produce water, which it says we don't care about that here. And we're also going to have a ton of the ClO2- ion being produced. So there you go. Letter C is your answer. All right. It didn't say to ignore the water here, but obviously there's no water choice, so it's irrelevant. So letter C is the correct answer for that one. All right. Really, really straightforward problem if you actually go through and take a look at all of your ions that are here and what's in the beaker and just do, kind of what I did. Process of elimination, see what's going on. You're adding a boatload of KOH. So you're going to blow through all of your hydrogen ion, and then you're going to also react with your weak acid that's here. Okay, one more. Again, pause it, and we'll give it a try. All right, so for this one, again, you could eliminate a couple answers here. It says you want to have an acid that has a concentration between 0.2 and 0.3 molar. All right, you have 100 milliliters of acid. All right. So let's think about this. If you have the same molarity of base, right? So super easy numbers to work with here. If the base is 0.2 molar. If your acid is 0.2 molar, it would take 100 milliliters of base. So 100 milliliters of 0.2 molar acid, we're just going to do HA, will completely react with 100 milliliters of 0.2 molar NaOH. All right, so if and the lowest I want my acid to be is 0.2. Remember, I want, like, this manufacturing process wants the acid to be between 0.2 and 0.3 molar. So I can get rid of A right off the bat, okay? Because I know, actually I can get rid of another one here too. I can get rid of B, all right? Because both of those are less than 100 milliliters, I need at least 100 milliliters of base to know that I have 0.2 molar acid. So again, you are gone with, you're done with two choices already. A and B, not a chance. So you're left with C and D. Well, if you added 200 milliliters of base, that would mean that your acid is twice as concentrated, right? So let's say your acid, let's say you had 100 milliliters of 0.4 molar acid. You would need 200 milliliters of 0.2 molar base to react with that, okay? So D is done, okay? That would mean, this one right here would mean that the acid is 0.4 molar, which is too high. So it looks like C is it, and we're done. Okay? All right, moving on. Another one I would have you do is a little more of a free response type question, but you have three choices here. Well, you have three solutions, A, B, and C. I give you a Ka value for carbonic acid, and I say, can you explain why you chose the order you did for ranking the solutions in order of increasing pH? So from the lowest pH to highest. Then find the pH of solution A, and then you're going to have to see which one has the smallest pH change. So take us a couple minutes here, give this one a try, and we'll go over it. Okay, so look at letter A. You have 25 milliliters of 0.1 molar H2CO3, it's carbonic acid, and 25 milliliters of 1 molar NaHCO3. As soon as you look at this, as soon as you make eye contact with this, you recognize this is a weak acid, and this is the conjugate base. All right, because the sodium for the 10 millionth time is going to be a negligible ion, so you're left with HCO3 minus right here. Okay, so there's a buffer solution. Okay, so we could easily figure out the pH of that in just a second, but let's see if we can just move on to some other ones first. Letter B, you have KOH, that's a strong base, and you have HCl, strong acid. So you take a look at that, you have 50 mils of 2 molar base, 50 mils of 2 molar acid. The volume and molarity is the same, completely neutralizing to give a pH of 7. Okay. Letter C, you have 75 mils of salt. You recognize NaCl as a neutral salt. Na+1 is negligible, Cl-1 is negligible. So that is not doing anything here. You have 75 mils of 1.5 molar hydrochloric acid. This is just going to be a strong acid solution. So the pH for this is way less than 7. All right, super small pH here. It's not a buffer solution because you don't have a weak acid and a conjugate. You have a strong acid and the conjugate, but that's not a buffer solution. So strong acid means the conjugates are negligible, and that's what we have here, a negligible salt. So let's actually look at letter A and find the pH of that solution. And that'll help us answer the first part of the question and actually address question number 2 as well. You have a buffer solution, so you automatically go to the Henderson-Hasselbalch equation. All right, so that is pH. This is on your equation sheet, but anyway, pH equals pKa plus log of conjugate base, conjugate base over the weak acid. Again, remember the shortcut here. When you have equal molarities of acid and base, this becomes log of 0. So that is out. So what you end up doing here is just doing pH equals pKa, and the pKa is the negative log of your Ka value. It gives you the Ka value down here. So if you plug it in your calculator, you're going to get a pH of 6.35. All right, so the lowest pH is letter C, and then letter A, and then letter B. Okay. Last one. A student adds 0.050 moles of a strong base to all three solutions. Which one has the smallest change in pH, and why? Well, this is pretty straightforward stuff. If you add the strong base to letter B, it's a neutral solution, so the pH is going to go up big time. If you look at letter C, you have a strong acid, so the pH is really, really low. If you add a strong base to that, the pH is going to start to go up by a substantial amount, right? Because you don't have as much of that strong acid anymore. So letter B and C will have big increases in pH. It says which one has the smallest change in pH? Just by looking at it, recognizing letter A as a buffer solution, I would automatically go with letter A because it's that buffer solution. Okay, and that is really it for that problem. All right, let's do one more and we'll wrap things up. All right, guys, last one of the day here. This is an example of a short FRQ, so you could see something like this. This style making its way onto the test whenever you guys are taking that. And it says the ionization of HF in water is represented by the equation above, and it gives you the dissociation equation. How nice. And it says in a 0.0350 molar HF solution, the percent ionization of HF is 13.0%. And it asks you a bunch of questions about this. So you can see there's only three parts to this, A, B, and C. The recommended time for a short FRQ is 9 minutes. So this should take you between 9 and 10 minutes if you're trying to stay on pace for the test. So I'll give you a second. You can, obviously pause the video here. Try to do this in 9 or 10 minutes, and then unpause it, and we'll see how we work through the solution. Okay, so the solution is posted in the answer key folder, but the explanation of it is going to follow here with what I have to go over with you guys. So letter A, in my opinion, is super easy points to get here. It says two particle diagrams, or two particulate representations of the ionization of HF in the 0.0350 molar HF solution are shown in figure 1 and 2. Water molecules are not shown. Explain why the representation of the ionization of HF molecules in water in figure 1 is more accurate than figure 2. And it gives you the key of where everything is. So remember, H3O is the same as H+, but they included their dissociation equation up here with water, so we're going to keep that in mind. Super easy question here, because HF is a weak acid. If you forgot that for some odd reason, it says the ionization, the percent ionization is 13%. That means 13% of HF breaks up into its ions, and the other 87% does not. So figure 1, we just answered the question, basically figure 1 has very little dissociation. Figure 2 has complete dissociation. Figure 2 would be the particle representation of a strong acid, but HF is not considered that, because the percent ionization is only 13%. Okay, so moving on to the next part, which is a little bit more challenging. It says use the percent ionization data to calculate the Ka. All right, so we have a weak acid here. I want to find the Ka value. So the only way to do that is to have a Ka expression. So that is obviously the first thing you should do here. So that is going to be F minus times H3O plus over HF. All right, so as soon as I do that, I recognize I need the Ka value. I don't have the other stuff. Icy table, it has to be. All right, so I'm going to ignore the water. I'm just going to put the icy table up here. I'm just going to shorten things up here. Okay, I'm just going to put H plus instead of H3O plus. It gives you initial molarity of 0.035. All right, so that's important. This is going to be a little cluttered here, best I can do. So the change is minus x plus x plus x. And then we have 0.035 minus x, x, x. But now think, it gave us the percent ionization of 13%. So that means I know out of my initial molarity, 13% is ions. Well, guess what? My ions are here, okay, in my dissociation equation. So let's actually figure it out here. So we have 0.0350 molar times 13%, which is 0.13. That tells me the ions are going to be, if you do the math, 0.00455. 0.00455 molar. That's the molarity that has dissociated. So that's X. So that's 0.00455 and 0.00455. Now, you cannot make the assumption here. You can't, this is clutter, I'm sorry. You cannot just say your equilibrium value of HF is 0.035. In order to make that assumption, we need the Ka value. Well, guess what? The Ka value isn't given to you. You need to figure it out. But you know what X is. So here, where my arrow is, try to clean this up a little bit. In that spot, you know that equilibrium value is 0.035 minus X, which is 0.035 minus 0.00455, because you have that. These look like sixes. I'm sorry, they're not. It's a zero there. So what you end up getting is 0.0305. It still looks like a 6. There we go. It's a little better. 0.0305. So in your Ka expression, you have 0.00455 times 0.00455 over 0.0305. And you get 6.79 times 10 to the negative fourth. Ish. Alright? So that's what you're going to end up with there. For letter B. So it's really not that difficult. You need to know what Ka is, so you set up a Ka expression. Then you need to go through and recognize you don't have a lot of that. You need an IC table. Go through the IC table. You know, it tells you the percent ionization is 13%, so you have 13% ions. The other 87% remains. So you still have very little product here, lots of reactant. Then it's a matter of, doing a little simple math, and you're good to go. Okay. Last part, letter C. I'm going to erase all of this on here because this is a little bit cluttered. Okay, 50 mils of distilled water is added to 50 mils of HF. Will the percent ionization increase, decrease, or stay the same? You cannot just say, I looked at all the various solutions here. A couple ways to do this, but you can't just say you're adding more water, so more is going to dissolve, because HF is a weak acid, so not a lot's dissolving anyway. So why would, more will dissolve, the percent ionization will increase. You're going to be able to dissolve a little bit more, or ionize a little bit more HF, but it's not going to be too much. So what you could do instead here is, since you're adding some water to dilute this, your initial molarity is different, okay? It's not going to be an initial molarity of 0.0350 molar anymore. So you're changing your concentrations really of everything here, your initial and your your other ions. So remember, going back to Unit 3, if you change your molarities, that's a stress to the system. Okay, so adding the distilled water is a stress to the system. You're changing the concentration. That's part of Le Chatelier's principle, right? So anytime you change concentration, you should focus on Q. All right, so I know we haven't used Q a lot, but Q is an equilibrium concept, and this whole unit is acid-base equilibrium. So we'll just look at how easy this is. Let's find a new Q value, or not a new, let's find our Q value in general of what's going on here after we have added 50 more milliliters of water. So Q is equal to, obviously, you have your dissociation equation up here. I'm going to put in 1/2. So we had 50 mils of the acid. We're adding 50 more milliliters of water. So we're diluting it, like we're cutting all the molarities in half. So we have a half times the concentration of F minus times a half times the concentration of H3O plus over a half of HF. Okay, so remember, like we diluted this, we diluted everything. So at equilibrium, everything's molarity, or not at equilibrium, but everything's molarity is cut in half here. So if we find Q, that's actually 1/2 of your Ka value, right? Because our Ka value is found by taking F minus, H3O plus, and HF, and putting those concentrations in. Well, if we cut all those in half, that's half of our Ka value. So obviously, half of your Ka value is less than your initial Ka value before this water was added. Okay? So when Q, so that's Q, when Q is less than Ka, the reaction proceeds in the forward direction. Well, if the reaction proceeds in the forward direction here, we produce more ions. Okay? That is how you're expected to explain this. Okay? It may not look like a lot of fun, or you might just want to say, well, I added more water, why can't I just say that? There needs to be some sort of calculation. Okay? It says, or explanation here. If you explained this process in words, that would be okay. An explanation isn't, oh, we added more water, so more is going to dissolve. Okay? So by adding more water, we changed our concentrations. That was a stress to the system. Okay? We found our new Q value, which is way less than our Ka value. So therefore, the reaction should proceed to the right, and more should dissociate. Okay? I do have the answer key posted in the answer key folder. There is another way to do this. That's to recalculate your initial molarity and to set up a Ka expression and to do your ionizations. So if you want to take a look at that, you can. This video is dragging on here. There's a lot to go over, okay? So even if you have to break this up, that's okay, into a couple different viewings. But take a look at the answer key that's posted in the answer key folder. You could see another way to do this, where you recalculate your percent ionization to get actually 20% ionized instead of 13, all right? It has to do with finding your new initial molarity here and kind of going from there. All right? If you have any questions, let me know, and we'll take it from there. All right? Thanks, guys.